Hello again and welcome back to Advent of Code 2025 in MIPS assembly for the PlayStation 2. Today we are up to day 2, which is called a gift shop. So we're inside this gift shop. We're going to be looking for invalid product IDs in the database, and we have this list of ID ranges that are separated with a with commas, and the range is separated with a dash, and it's a single line in the input. So invalid IDs have a sequence of digits repeated twice. They're made up of a sequence of digits repeated twice. So 55 is 5 twice, 64, 64, 64 twice, 1, 2, 3, 1, 2, 3, 1, 2, 3 twice. There are no leading zeros, and it has to be the entire ID, right? You can't just have a sequence at the start, which is repeated twice, and then junk on the end. It has to be the entire ID. Yeah. Right. And so this is my puzzles for the first part. The second part has to be repeated at least twice. Right. So this one here, 1, 2, 3, 4, 1, 2, 3, 4 is twice. You got 1, 2, 3, 1, 2, 3, 1, 2, 3, 3 times. This one here is 5 times. It's 7 times. And so I've got some more examples here and my final result down here. So the important thing to remember, or sort of point out here, is that in the first part it has to be an even length, right? You have to have an even length ID number to be potentially valid, potentially invalid, right? Because you have to be able to get to split it in half and have both sides to be the same number. In the second part, it can be an odd length, because like this one here is 7 times. This one here is 9 in length, so you have 3 repeats. Right. So if it's an odd number of repeats, and an odd number length sort of thing, yeah. But it doesn't have, well, whatever. Anyway, so unfortunately I didn't do it a very good way in my solution, but we'll go and have a look at the solution now, shall we? All right. So let's see what we're doing here first. Okay, start off basic same as last time. We've got clearing out ASCII num, and I've got the input start and end pointers or locations in memory set up there. We go into the input loop. We're checking if S6 is less than S7. Got that right. If it's equal, then we go to check range. If it's equal to 0, then we branch to check range. Set less than S6 less than S7, whatever. When we load S3 with A0, we load that byte into there, and then we branch there to check range as well. I'm not entirely sure why I'm doing this up here. That seems a bit weird. That does seem a bit weird. Anyway, it probably conks out in the end anyway. Well, that's going to get loaded no matter what, whether we branch or not. So we load the byte. This byte is coming out of the input text. If that byte is OA, hex OA, and so the end of line character return character, then we go to check range. Otherwise, we load S3 with 2D, which I think, which one was it? I think it was the hyphen. If it's equal, then we go to check range to that, and then 2C, which would be the comma, so comma and the hyphen, 2C and 2D, and if it's equal to that, then we go to check range. If it's not equal to any of those things, then it's going to be one of the number characters, and so then we load from ASCII num, right? S0 has the address of ASCII num there. We load the length, length value at the start of ASCII num. We add 1 to it. We store that back, and then we add that length to ASCII num's memory address, and the value that we loaded here with OF to get the digit itself, 0, 1, 2, 3, 4, 5, whatever, and then we store that on the end of ASCII num, and then we increment S6, which is our pointer, and we go to back to the start of the input loop. So if we get down to check range here, we jump to convert to ASCII, conv-asc, and then we check, again we're checking, like we load S2 there, S3 will be what was in, oh no, here we are, S3 was the last thing that we loaded, this one here. So if that ends up S3 is equal to 2a, then we branch, it's not equal to 2a, then we branch to incat up here. Otherwise we'll just fall through out this way here. So it is a way of exiting. I think essentially what I'm doing there is, if it's detecting the final value on the line, right? Because this here ends here. If it ends with a carriage return, then we go down to, actually I think I even made it, I forced it to be a carriage return to make sure that I went down there. Oh no, wait. Ah, that's right, of course. Wait, so I sort of messed up something here. Right, if S6 is equal to S7, if S6 is less than S7, then S2 will become 1. It will come out as 1, and so it won't branch. But if it is less than S7, then it will branch. So that's when there's no carriage return on the end of the input. Okay, yeah, that's right. There we go. Yeah. So that's detecting the end of the input, but there's no carriage return, and so it needs to go down to check range anyway. Yeah. But I load in this one here to make sure it's here to do this check, so it can exit out, so it can skip going back to input loop increment and go straight to finish date. Yeah. So that's what I'm doing there. Anyway. So yeah, so we're going to, everything else now goes into this convert ASCII. So what we've got going on here, I back up a lot of registers, it was coming, and I'm doing this conversion here a stupid way. I've got these, I'm doing like a 64-bit conversion sort of thing, like, because we get some very big numbers here, I need to be able to handle 64-bit input numbers. And so if you're doing 32-bit multiplication, which is what, well, you do the multiplication here with 32-bit input numbers, and you can get out 64-bit by having a high and a low register, right? When I do it like this with a register here, it stores the low result into this register on the way out, and then you have to restore the retrieve the high from the high register with this move from high. But this is really stupid that I'm doing it like this, because as I realized like a couple more days in the future, all I have to do is loop a multiplication by 10. And you can do an easy quick multiplication by 10 by first shifting left 1 once, one place, and this shift left will shift left 64 bits. Or yeah, shift the whole register. Well, I say the whole register, but most of these operations, all the registers on the PS2 are 128 bits wide, but most of the operations act on the 64 bits of it. So you would lose the top 64 bits anyway. So you could do a single shift left, copy that, move that value into another register, then shift it left 2 more spaces, and then add that other register back to the those registers together, and then you have that's a multiplication by 10, right? And then you can add, and then I can go through and add this value here, this byte, the value of this byte to that, and that multiplies by 10 and adds in the new ones place, and then you just loop that all the way through, and you'd have your either well, no, yeah, which way was I doing it? Yeah, no, because what I'm doing here is I'm going from the ones and I'm multiplying the 1 by 10 by 100 by 1000 and adding it to the result. But instead of that, if I go from the top and I say multiply the result by 10 and then add the top digit to it, and then loop down it, multiplying it by 10 and then adding the digit in that place, then that way I can also get the value into a register in binary format, and you don't have to use mults, which are, I think they take about 6 cycles compared to just 1 to do like a shift. So shift left takes one cycle, move to another register takes 1 cycle, shift left again takes 1 cycle, add together takes another cycle. That's 4 cycles compared to like this. Actually, we'll go down to like about here, you know. That's 4 cycles compared to probably like 20, right? Actually, I've got a couple more in here. Might be more than that, like 30 or something, right? So it's much faster and it's much cleaner and easier to do, much less complicated, and you have to use less registers for it and stuff as well. So all around it's better. I completely forgot about it. I learned that with the 6502, and then once I got the multiplication like register, I just started multiplying things instead of using, you know, those simpler techniques to move things around, which is kind of an Achilles heel of doing things in assembly. That the optimizations, like if you can use like C, you did it in C, you did that sort of conversion, type that conversion up in C, it would probably optimize it during compilation into one of those much faster optimized loops of just bit shifting to do the multiplication. But because I'm hand writing it, if I don't think of the optimization, then I lose it, right? I don't get that. So yeah, it's kind of a mistake of trying to go my own way in assembly. So yeah, what I'm doing here, I've got a high multiplier for the top 32 bits, a low multiplier for the bottom 32 bits. Oh well, low, bottom, high, top, whatever. 10 for the 10's multiplier, because I have to multiply by 10 every time. This one here, what was this? Load from S0. Okay. What was S0 again? What do I have on? That'd be the ASCII now, wouldn't it? Ah, right. So this is the length of my input, right? And where I'm starting. Actually, it's where I'm starting. Reading from. Yeah. Which is the last digit in the input. This is where the final result comes up from, right? So I load the byte, the value, the digit, and I multiply the upper and the lower. No, I multiply it by the upper and lower multipliers, right? Then I have to shift off the top. If what I've got here, if so this is the top result, I think. No, this is the low multiplier. I have here that I want to like. I think it's because if I end up on the top bit, it can do a right. I think that's right. It tends to do a sign extend. So if I end up with like a 1 in the highest bit of the 32-bit result, it will sign extend out to the whole, fill up the whole 64-bit register. And so I have to make sure that that doesn't happen. So I get rid of, I shift it to the left 32 bits and then shift it back, and that will get rid of anything that's in those top 32 bits. Should that happen, and then I move the high result into S5, and I add that part from S5 to T2. I shift that, undo that, shift that to the left 32 bits, because the double shift left 32, and so by shifting it left 0 steps, it actually just shifts it 32. So the SL or DSLL, you can shift it from 0 to 32, 0 to 31. 0 sounds actually a silly way of saying it. Like from 1 to 31 places to the left, and if you want to shift it 32 to 64 or whatever places to the left, then you have to do DSLL 32. Right. Anyway, and you get 0 to 32. And then I'm adding these together. So I add the top to the bottom, and then I add that to S4. And then I multiply the two multipliers by 10, right? And then we add, if there's a high part of this part here of this result, then we add that to into here. That doesn't seem right, because that'd be the high part of this one here. Oh no, that is right. No, that's right. That's okay. Yeah, that's alright. Is it? No, I think that's wrong. But it comes out alright. Oh no. No, I think I should be adding that to S7, shouldn't I? Who cares? Who cares? It works. So, like, it's convoluted. This is why I'm like, this is like a dumb way of doing it. Because it's kind of convoluted. I'm like, wait, is this the right way of doing it? Yeah. Yeah. Anyway, and then we loop through it and go to the next digit, and well, we subtract 1 from S1, and if it's not equal to S0, like if S1 is not equal to S0, then we go back through the loop. If it is equal to S0, then we're done, and we don't want to go through the loop, and we clear out the value that was in ASCII num. And so now what we do next depends on the value that was in S3 when we came into this convert ASC, right? So if it's not equal to 2D, then we're going to branch to store right. But if it is equal to 2D, then we're going to store it in the left part, and then into this value, this memory position, this memory place called left, and then we'll jump to convert ASCII end. So we'll just store the left half of the ID list, the ID range, but if it's not equal to 2D, so if it was 2C or OA for the end of the input, then we'd go into the store right part. So we'd store that at this memory position right, and then we'd jump to find invalids, and then assume when we come back from that, or if we've jumped, we restore these values from the stack and the stack pointer. So the rest of this is the find invalids part, right? So we go in here, backing up a lot of these again. We've got these two values, the left and the right of the inputs, and we've got this silver loop here. So essentially what I'm doing here, my dumb solution for this is that you can you can divide by, let's say, if you divide the ID by 10 and the divisor and the remainder are the same, then it's an invalid ID, right? If you divide it by 100 and it's the same, it's an invalid ID. If you divide it by 1,000 and it's the same, it's an invalid ID, right? What you have to divide it by all depends on how long the number is, but we don't really know how long the number is anymore because we've just got it in binary. And this is the dumb thing I'm doing, where I should have probably kept it as a decimal string like this, or binary coded decimal, and then used something like the lengths to determine whether I even bother checking for the silver part if it's a potentially invalid ID, because if it's an odd length, then there's no reason to check, right? And it would have made it much easier, I think, really. But I did this stupidly, so we have to live with that now. So I think what I'm doing here is that I've essentially just got this loop, and I'm like, hey, once it gets, once our divider thing gets too big, right, exit out of the loop. And we haven't found a solution. Just exit out of the loop. And so I'm doing shitloads of division, and it takes a stupidly long time, and it's the worst way of doing it. Anyway, so what I do here, so I've got this previous divisor and the current divisor, right? So we go, I'm going to shift it to the right 31 spaces. If it's not equal to 0, so if you've still got the divisor, which remember this S5, which is this thing here, if there's still a value in S0 after we've shifted S5 right 31 spaces, then we're done. Just say we're done, we're out. If S5 is less than, let's go, we set this if S5 is less than S6. So if the value of S5 is greater than this value in S6, which is the ID that we'll be checking, then we also branch out. Because, you know, if we're checking the number 20 and I've divided it by 10, there's no point dividing it by 100, because, you know, there's no point dividing it by 1,000, there's no point dividing it by 10,000, right? This is another way of getting out faster, right? And so we do this jump to long division, and then I've got this thing here go like, I think these are some of the results that come back. If set S1 is less than S4, I think S1 might be something that comes back out of long division here. I need to do a little check on that. So if S1 is less than S4, so set S0 if S1 is S4, right? If this is not equal to 0, so if this is true, S1 is less than S4, then we branch to the next div. If they are not, if S1 is not equal to S2, then we branch to SDiv as well. So let's see. I think S1 is the divisor. So what was it? If S1 is less than S4, alright, so that's the previous divisor there, right? So I think I'd have to take in this thing, like, if, let's say I've got the value like 999 thing here, right? And I'm divided by 100. If I divide it by 100 and this value here, right, is now less than 10, there's no possible way that it's equal, right? That this side here is equal to this side here. And I need to, but then why do I go to the next div? Well, yeah. It's a new day, and I've realized exactly what I was doing in this check in the code. And obviously I'm flailing to explain it in the video, so we'll just interject here for a second. Okay, so let's ignore this 999 example here for a minute. Let's take 909 as the example, right? So let's say I divide 909 by 10, right? You end up with 90 remainder 9, right? So that's not the same number. So I go to the next round and I go divide by 100, right? And what you'll end up with is 9 with a remainder of 9, right? So that would appear to be a invalid ID because you've got 9 on the quotient, 9 on the remainder, right? But 9 is less than the previous divisor, which is 10. So what this is doing here is it's checking that the remainder is not less than the previous divisor, so that I don't have this sort of situation where there's a 0 at the top of, you say at the top of the remainder, that is reducing the size of it, right? Yeah, and erroneously picking up matches. So that's the reason for this check. That's the reason for this check. The entire reason for keeping track of the previous divisor. All right, back to flailing to explain the rest of the video. Go to next div. I think I might be a way of like making sure that I don't end up with like a 0 in here and a 0 on the other side and them going, oh, okay, that's the same number or something. Which shouldn't happen, but yeah. I don't know. Not entirely sure, but it makes it work. Another thing that it's like probably solved a case that I had going on, and I'm not entirely sure why it's solving the case, but anyway. But then here's the check to make sure that both sides are the same. If they are both the same, then we, if they're not the same, then we go to next div down here. Otherwise, we'll be adding the value. Which again, we'll have to load the value out of left again. Wait. S6. Alright, S6 is the present value for left. Right, and we add it to the silver result, and we store that back in. We go to next silver. I jump to next silver. Which which goes back into the next silver loop. Of course, right. Yeah. Because next silver will add 1 to S6 to go to the next possible ID number. And then we've got the next div here where we multiply the divisor by 10, right? Flowing those, adding on the high result if we need to, the high to the low if we need to. Yep. Then moving S5 into S4, the previous divisor, the current divisor into the previous divisor, and then S0 there goes into S5, the new divisor, and goes back to the div loop. Okay, so let's have a look at the long division thing, shall we? So that's basically all of the silver side done. The long division is used again further down here. So anyway, so here we go. Yeah, returns the quotient in S2 and the remainder in S1. So I've got the remainder. So here's if the remainder, yeah, I've got written here in the gold part. Yeah, if the remainder is less than the divisor, then we've got a problem. If the remainder is less than the divisor, the remainder has to be less than the divisor. Okay. Interesting. Don't know why. Anyway, so long division here, backing up a lot of registers again, right? And I call this long division, but at first it's going to check to see if we have to do a long division by shifting the input right 32 spaces. If it's 0, then we don't have to do a long division. It's going to be a 32-bit division, so we just do this div and we move the high into S1 and the low into S0, S2, and we go back and we jump out, jump to long division end. Otherwise, what we're going to do is a loop of 4 16-bit divisions. We're going to split the value into 16-bit chunks and move the remainder from each division into the higher 16 bits for the next step of the division. And that allows us to divide up to 64-bit numbers. So we set this here as a limit, S0 as a limit. We move zeros into S1, T1, we divide S5 by S0. So this helps break up because we're doing 16-bit divisions, we need to have up to 2 divisions, 2 rounds of this. Say if we go up to, because I'm going up to like 10 million, so by having like 10,000, it's like 10,000 by 10,000, right? It gets you up to like 10 million. So we divide whatever the incoming divisor is by 10,000, and we might have to do two sets of division. So that's what I end up doing here. It's a hacky, annoying, stupid thing that I'm doing here, but it works. It ends up working, right? So let's see. So we move the high into S5. If it's not equal to 0, then we branch straight into long division, which will also flow load the low into S0, and then we load S5. If it is equal to 0, then we end up loading 10,000 to S5. So we'll do the 10,000 first. Anyway, so we go into here. This is a mask that we use to chop off 16 bits of the value. How much we're going to shift, 48 bits first, then 48, and then we'll subtract 16 from it. So 48, 32, 16, 0. I think there's 0 in there. Yeah, there's a 0 there as well. And we're going to load up these V0, V1, and S2. We're going to use those. So then we have this long division loop, and it's much the same as what I'm doing for my result, which I go over in the introduction, right? We shift this by S4, the input value, the value that will come in by S4, so 48 bits. So we shift it right 48, and we AND it with this mask, so we just get those 16 bits that we want. And then we shift left V0 16, which is like the previous remainder, and we OR them together. So if there was a remainder from the previous round, then we bring that into the top 16 bits. If it's equal to 0, don't do a division. Otherwise we do the division here, and we get that remainder on V0 and the quotient on V1, right? And then we're going to shift this back by the amount that we did here, if we have to. We OR it with S2, which I think is our result sort of thing. If S4 is not equal to 0, right here, then we go for the next round of the loop, and we subtract 16 from S4. Right, so we're going to do that 4 times, that section 4 times there. And then we've got this thing down here, if T1 is equal to 0, then we skip this long division skip mult. We load S5 with 10,000 anyway, and then we divide we multiply V0, which is our quotient, by 10,000. Oh. And I believe that there is for the second round, right? Because we do that to divide it by up to 10,000. Well, because if we want to divide it by over 10,000, we have to go through this loop twice. And so if we do that, then we need to multiply the result we got out at some point by 10,000. And this one here, like I think it's the first time through, if it's equal to 0, then we skip the wrong result. So if it's the second time through, the first time is always going to be, like if the divider that we're doing is above 10,000, then the first time through is always going to be the 10,000, right? So the second time we come through, we want to multiply the result from the last time by 10,000 before we add the result from this time to it. So do the adding of the result into, we add one to T1. This is one here, we're seeing that flag essentially. We add the result into it, or whatever. Then we set some more things to 0, and if S5 is not equal to 0 here, so that value we took out of S0, which was set up here somewhere, yeah, up here, right? We're deciding what we're doing essentially. If that value that we got out of there was not equal to 0, then we go back up and we do the division again. Otherwise, and then we set it to 0 to make sure it's zeroed. And once we're done, we just exit out of this, right? And so what would end up happening is that S1 and S2 have our final move S2 into there, S5 and S6, that's right. So I move those into S5 and S6, which would be used in the second round of the division. But otherwise, S1 and S2 end up being, see, they're not restored when we exit out of this long division. S1 and S2 end up being the result, the quotient and the remainders. Right? So that's how that long division works. If clear as mud, probably pain in the ass to follow. Yeah, but anyway, yeah, you get the quotient and the remainder of doing that division back out. Alright, so that's the silver part. Then I load the value again into S6 and we try the gold part, which is a kind of a copy, except there's like an extra loop in here, I believe. See, I've got this loop current div. Yeah. So we've got here the last remainder, S3, but otherwise most of the stuff at the top is the same. We back up S6 because it will get changed as we do some divisions through here, I think. So we back that up just to make sure. The stuff up here is the same, except that we jump to next gold and next gold div. So I think up here, yeah, both of these are next silver, and this one here is next gold div. Right. So essentially, if I get to like, hey, we've got S5 is less than T6. Ah, yeah, that's right. I see. Then we want to try the next division step. We'll see as we get through this sort of thing. Right. So I've got this branch to the long division here. As normal, if the remainder is less than the divider, then we go to the next gold div. If there's no we check here if we've got S0, set S0 if S3 is less than F0. So we only get to here if S0 is 0, right? Because we've set it over here. If it was 1, then we would have branched. So we only get to here if S0 was 0. So if S3 is less than 0, then we skip prev check, right? Otherwise, we're checking if the remainder that's come out of the division was the same as the previous remainder that came out of the division, right? So let's say, like, let's have a quick look over here. Like, if we're dividing this one here, the 1, 2, 3, 1, 2, 3, 1, 2, 3 by 1,000, then the first remainder that comes out should be 1, 2, 3, will be 123. Then the second remainder that comes out, once we divide this one here by 1,000, this remainder here should be 1, 2, 3. Then we'll divide this by 1,000, the remainder should be 1, 2, 3 again, right? So I have to check if each remainder is the same as we come out. And so that's what we're doing here, right? If it's not the same, then we try the next step in the division, right? We try the next division step. Like, instead of dividing by 1,000, let's divide by 10,000 and see what happens, right? And then we have to go back to next div check. Where was the next div check? One down. Next gold div. We have to restore S6 back into what have we got here? Oh yeah, we move T6 back into S6, and then we do that multiplication to multiply the divider by 10. All the same as the silver one. And then we go back into the next gold loop thing. Yeah. So if those are equal, if those are not equal, then we try to loop the current division. So the remainder is the same as the previous remainder, but the quotient is not equal to the remainder yet. So we want to loop. We want to try loop it again. And so we jump over to the gold loop div. Yada yada yada. So we want to divide. We want to divide this. And so we end up moving the quotient into S6. So if I divided, this by 1,000, the quotient would be in this part here. And we move that into S6, and so then we'll divide this by 1,000 next time. Right. And then we move, we also move the remainder into S3. So that doesn't need to be done if it's the same as the previous one, but we skip if it's 0, so we have to move it anyway. But if they were equal, the quotient and the remainder were equal, then we're adding it to the gold, right? The gold result. The next gold div down here. If any time it sort of fails, then we want to go further up through the list of gold divisors, multiply the divisor by 10, come into here, multiply that divisor, and then any time that we don't find an invalid ID, we want to restore that value from S6 and then increment it and then go through the gold loop again until where was it? We don't have my way out of this. It is here actually, yeah. Until S6 is equal to S7. So once it is equal, and I've got this increment after this branch, so that when S6 is equal to S7, it will branch, and when it's 1 less than S7, it will decide to branch, and then it will add 1 to it, and so it will check the final value, the right hand side value. It will check this value here. And then we get to the invalids end. And that's all of it. Alright, so that, hopefully that is all clear as mud. Let's run it. And let's see how we go. So I'll bring up the emulator here. We've got it ready to go. Unpause that. And I'll run this here. And it is quite a bit slower than the previous day, and I think this is the slowest one of the solutions that I did. And it's understandable because I did it so poorly. Alright, so we can see that the result down there is correct for the bottom one, and if I move up here to there, we should also be able to see it is correct for the top one. Alright, so that was day 2. Probably the worst way of doing it, and I think right now I'm going to say that it is my intention, after I'm done with the going through these days that I completed, I will come back and I think I will stream redoing this solution the better way. I'm not going to say the proper way, the better way. Yeah, I'll come back. I think I'll stream it. I'll stream it doing it live, writing out a better solution for this. Keeping it in binary code decimal, and instead just like loading chunks and comparing them together in a better way. Hopefully it won't take too long, but we'll see how it goes. Alright then, so until the next time, I hope to see you again in day 3.